Let's have the next speaker will be introduced by our Vice President, Karolina Sulic. It's a wonderful and beautiful. I want you to pay attention to the slides that I think will be very pretty with really beautiful crystals showing. And can we have the screen back on, please, with MIT AV?
Oh, sorry. So hello, everyone. I would like to introduce Professor Cecilia Roque, who is Associate Professor and Researcher at Nova School of Science and Technology. And I see you, Professor Cecilia, on the big screen, so we can probably hear you in a second. It's wonderful to have you with us again. Please, the floor is yours.
Okay, so good morning for you. For us, it's already afternoon, so thank you very much again for this nice invitation from Andreas and Carolina. So this is a really fantastic community in Osmocosm. I think it's always super inspiring to be at this conference and to attend and listen to the talk. So I'm just going to change a little bit the topic from our previous speaker, although it's obviously all related. And so my short intervention today will be related with scents in the drought. What I want to basically call our attention, it's for, let's say, an universal problem that is typically seen when we deal with chemical sensing of volatile organic compounds. So my talk, it's related with the sense of a smell, of course, but in the perspective of developing sensors that can actually detect these volatile organic compounds. So we look at them as small molecules that are chemical analytes, and also they are represented here by these, circles and squares, etc. So they are all slightly different in their chemical functionalities and also a little bit in the size, so they have different chemical properties, and these are the properties that you need to somehow be able to pick up in when you develop a sensor. There is, however, a general problem that we have with chemical sensing of volatile organic compounds, and this is the problem of humidity. So humidity is, so it's basically present in our ambient conditions, and also it's particularly important when you want to analyze volatile organic compounds that exist, for example, in body fluids. So we know, for example, it can be in the breath, it can be in urine, it can be even in blood or plasma, and in all these biological fluids, we have about 91 to 95% of humidity. So it means that in reality, when we are trying to analyze and detect particular volatile organic compounds or fingerprints of volatile organic compounds, it's almost like looking and trying to find, a needle in a haystack. And so there are several ways to try to deal with this issue. So when we have the implementation and development of electronic nose devices that mimic, as we know, try to mimic the behavior and the functioning of a normal nose, we have these electronic nose sensors. So the sensors are basically made up of materials that need to change properties in the presence of volatile organic compounds, and these changes in these properties give rise to signals, and these signals are then basically processed and analyzed and fed up into machine algorithm, for example, algorithms, or you can even use other statistical approaches. But nonetheless, how do you deal with this problem of the high content of humidity? So typically you can try to dry out your sample. So in the beginning, you just try to dry your sample before the sample enters in contact with the electronic nose sensors, or you can then try to deal with the data. So you can try to somehow clean your signals and remove or minimize as much as possible the influence of humidity. And I'm just going to present a work that we have done related with the modification and the tuning of the materials that we use for the electronic nose sensors to try to tune the influence of humidity. So for this, we have basically tried to develop an electronic nose like a cyborg, as we have in this image, that could either work in dry or humid conditions. And so the basis of this work is on the type of materials that we used to build the sensors. So we have used materials that are based on ionic liquids. So I don't know if you are aware about ionic liquids. They are basically made up of a positive and a negative charge. So they have a cation and an anion, and they have very important properties. Firstly is that they have very low vapor pressure, which means that they basically do not dry. They have high ionic conductivity and also a very high chemical diversity, as we can see here just in these examples that I've presented. And we can use these ionic liquids basically to dissolve certain polymers and materials and make what we call ionogels. So ionogels are basically this type of materials that are a 3D network that basically results from the entrapment of the ionic liquid within a particular matrix. And the interesting thing about the ionogels is that they maintain the same properties as the ionic liquid. So they have low vapor pressure, so ionogels do not dry out in comparison with hydrogels. They also have a very high ionic conductivity, which can be interesting to, get an electrical signal from these materials. And this is what you get when you use them as electrical sensors. And we can use different polymers or molecules to actually assemble these ionogel matrices. So we can use, for example, polymers as gelatin, that give rise to this type of yellowish ionogels that we have here. We can also use, for example, other type of polymers that we isolate, for example, fibrin that comes from this Bombyx mori insect, or we can also even use, for example, peptides that are much smaller molecules. But the example I'm going to present is related with gelatin. So the gelatin that we used for cooking. And in this particular case, we dissolved and gelated gelatin in the presence of two different ionic liquids. So these ionic liquids have these positive charges constant, the meme plus, and then we use two different negative components. One is called the DCA minus, and the other one is based on chlorine. So the difference here, it's only the anion. And the reality is that chloride is actually much more hydrophilic and much more hygroscopic. And this made a complete change in the optical and the electrical signal of this type of ionogels. This year, I'm just presenting here the results for the electrical signal that we get from this type of materials. And what we could see is that in the case of DCA minus, as it is much less hygroscopic and hydrophilic, it's much better to detect volatile organic compounds, both in dry and humid conditions, which does not happen, for example, with the chloride, because in this case, we have a large competition of water molecules that like to bind to this chloride and ion. And so this type of ionogels with the chlorine and ion are not so suitable for sensing volatile organic compounds. So this is just the summary of this short talk that I bring this year. So it's related with the tuning and design of the ionogel materials, their composition, in this case, changing a single anion to make the materials more suitable for volatile organic sensing in dry and humid conditions. So it's everything. So thank you very much for the opportunity. Well, I'm happy to answer any questions you may have.
Yes, thank you, Cecilia. That was very powerful. I always love seeing your lectures. I have the effect of humidity and water on the ability to sense VOCs. We've known this for many, many years that, I'm sure you know this too, that dry air doesn't smell. A wet dog smells more because of the volatilization of the odorants that are stuck to the skin and the fur. Now, is it possible to get around this problem that any electronic nose will be affected maximally by relative humidity fluctuations by actually tracking the relative humidity and deconvoluting it from the signal? Meaning that if you put a little humidity sensor right there in line with your noses, can you deconvolve the effects of humidity and still recover some of the signal of the VOCs?
Thank you, Andreas. Of course, this is one of the approaches that is done at the moment. Usually the difficulties are, in using this approach that is valid, okay, in certain situations, is that sometimes your volatile organic compound really exists in very low amounts in comparison with the amount of humidity that you have. So the interference might be so high that it's difficult to make this deconvolution. But of course, I think it needs to be seen on a case-to-case. It's not like a universal.
Yeah, it's a fair answer. From my experience, if I can share, it might be of help to you. When we do this to my nose, which is with the immobilized GPCRs, it actually works perfectly for us, but we've only taken, well, we actually taken it pretty low, but it's a very different technology than yours. Ours is a field effect transistor. So for us, having a humidity trace is essential. In fact, we found out that most of the noses built electronic noses were basically very expensive humidity detectors, because as a first step in a field effect transistor geometry, what happens is the odorant displaces water molecules or adds the capacity for the sensor to have water molecules adhere to it, depending on the orientation and all that. So you can see these giant fluctuations in humidity, which of course overwhelm the signal unless you take them out.
Sure. Yeah. And to be honest, I mean, we agree completely with your view. We think that we should deal with the humidity that exists instead of trying to remove it. And for example, in our particular case, we also need a certain level of humidity for the sensors to work in their best way. I mean, although we don't use biological components as you do, but I think we better try to tune our materials and our sensors to deal with the humidity.
Yes, thank you for that. Unless you have questions from the audience or from online. Oh yes, there's one question from the audience. Here, let me give you the microphone. Go ahead, and welcome. I know where you
are. Is it possible at all for there to be a section of the sensor where humidity is entirely equalized, where it reaches an equilibrium by either inserting more vaporized water into a section of the sensor earlier on, or decrease the amount of the humidity, so that way you can like stabilize all humidity rather than have to denoise it later on? It wouldn't be easier to do that ahead of time rather than after the fact?
Exactly. I mean, thank you for your question. That's exactly one of the approaches that I have indicated. I mean, you can try to somehow dry your sample before it enters in contact with the sensors, and you may do a complete removal of water, or you can try, as you were suggesting, to somehow take the humidity to a certain level that it's sort of, more or less constant. It's not very easy, depends a lot on your setup, but I mean, obviously that's one of the approaches that you can take, and we've been also working a little bit on that. So trying to have it at a certain level that it's always the same, so you don't have so much fluctuations.
Got it, thank you.
All right, let's thank our speaker one more time. And,